Now we are on the study guide part 3. We're talking about gas laws from chapter 11. We didn't cover those, but there's a few problems, 5 problems on this on the test. You don't have to know them, but it's if you want to really strive for the best, then I'll explain this to you. Many times when you perform a reaction in a beaker, there's no gas given off. But sometimes you're going to have gas coming off of a reaction. And we need to know everything about that for just one simple reason, is that gases are dangerous. If it's in a beaker, it's fine, but if it's in a pipeline that's stretched over several miles, or if it's in a pressurized container in a plant or something like that, we really need to have precise control over what gas is doing. After all, whenever we hear boom from TNT, C4, and other explosives, it's really the rapid motion of gas that, together with heat, that causes all the damage. So there's actually lots of merit to knowing about gas laws. One thing about gas laws is that we will be looking at all the reactions here, all the problems here, from point of view of container. So you usually have to contain a gas in something. Why? Because if you put gas into a container, then you know it's pressure. So pressure of gas is the measure of the amount of gas. And because in chemistry we study matter, and matter has mass and volume. Its mass that is related is the amount of substance that is related to pressure of a gas, because number of molecules, moles, and the more moles of gas we have, the higher mass of gas we have inside than our particular gas, then the higher pressure we have, and that's why we do that. But when we do study all these things, our container is usually a piston inside of a cylinder, which can be visualized as a syringe, which has a plunger. Plunger is the piston, and why we do that is because we can gauge the volume, both volume and pressure or something. So when you do this reaction, just imagine a huge syringe. Essentially, that's what happens. Because we can vary the volume by increasing the pressure. Sometimes when we push the piston down, the plunger down on a syringe, we see resistance because the pressure hasn't increased. And if we pull this out all the way, we'll see it will be sucked in again because we're producing a little bit of vacuum. So that's the bottom line, is that we need to know that we're studying gas, which is pressure is the measure of its amount, and ultimately for us, and we're looking at everything from the point of a container, which is our syringe with the piston moving up and down. Another important part to realize is this a formula type of solution. It's not conversion factor solution, it's a formula solution. And the formula that you need to know is right here. And so in this case, R is equal to PV over NT. This is pressure. This is volume. This is temperature. In Kelvin, not Celsius. This is moles of gas. And pressure is in atmospheres. So R is a constant. It will be given to you on the exam. It's a gas constant. And one thing you need to memorize is that 1 atmosphere is 760 torr. Same thing, torr is same thing as millimeters of Hg, mercury. So let's look at some of the problems. As always, in terms of formula problems, we have to inventory what we're dealing with. So we have a problem 23. A sample of gas has an initial volume and a pressure of such. If the sample is compressed, which means that it decreases volume to 10.9, what does the pressure be? So in that case, we have initial state and final state. Our main equation is R equals PV divided by NT. And this is a constant, therefore what we're going to do is going to say this P1, V1, N1, T1 is going to be equal to P2, V2, N2, T2. They're equal to each other because they're equal to the constant, our initial state, our final state. Let's see what we're dealing with. We're dealing with volume. And what else are we dealing with? Pressure. And we have to find the final pressure, but we're not given T or N because they must be staying the same. So I'm going to cancel these out on both sides of the equation. And that equation becomes P1 V1 equals P2 V2. See what we got here. We have initial volume, we have final volume right there, we have initial pressure, second pressure, that is going to be my X. So therefore I'm going to put that solve for X in my case, and I'll have 1.7 times 26.6 equals X times 10.9, and we'll solve for X, then plug it in. The problem 26 involves the idea of partial pressures, which is if we have a container, as always, and we have different gases floating around. Now, each one of those gases is hitting the walls of the container. And it turns out that so each gas contributes to the pressure. Therefore, the sum of the pressures of the inside of each gas contributes to the total pressure, say, of 11.0. So here we have helium and oxygen. So imagine this is helium, this is oxygen. And the total pressure, P total, is equal to partial pressures or contributing pressures of individual gases like helium plus oxygen. And so we are asked to find the partial pressure of helium. We don't know, that's my X. We do know the total pressure, and we do know partial pressure of oxygen. So therefore, 11.0 is equal to X plus 0.30. And we just have to solve for X, plug this in, and we'll have our solution. Partial pressure of helium. In this particular problem, problem number 27, we have a mixture of gases, and these are the gases that we have. Here are our partial pressures, and question, what is our total pressure? Well, to do the total pressure, you have to sum all of these up to get my total and plug this in. Sorry, wrong arrow. In this problem, number 28, we're using R is equal to PV over NT. We don't have an initial state or a final state. This is what it is. We're given everything except for one variable. So in this case, we have everything but n. So we have to solve for n. N will be x. And then in this case, we're given everything but v. So we'd solve for v would be x, and so on. And don't forget to convert torr to atmosphere. By the way, R can be found in the back cover of the book.